My subject is extinctions, but you'll notice the subheading. So it's not all the doom and gloom of the extinction itself, because clearly life has survived through many extinction events. And I think most of you know that, in fact, some of the biggest mass extinctions have given big opportunities to the survivors. So we're going to have a look at that theme. And another theme is going to be, how can we study these things? How can we have any kind of understanding or certainty about events that happened a long time ago in the past? So let me see if I can. There we go. So one question would be, why do we care? I think as geologists, of course, we know that this is a very important theme, but many other people, many members of the public might think, well, it's just about dinosaurs and it has no particular relevance. However, the relevance, of course, is to the whole theme of biodiversity, which I think we would class as one of the most immediate scientific themes that anybody from the age of 3 or 4 upwards would think about. As for the future, how will biodiversity fare? And when we look at this kind of image, we think of the great diversity of life on Earth and the incredible value and the incredible range of organisms that we know, of course, as geologists, track back through many ancestral forms. We know that, of course, extinction isn't all caused by humans. So it's important that we have that context, which a lot of people might not have, and that we do expect a certain amount of extinction to happen. In other words, species don't last forever. And typically, we think of species as maybe lasting for 1,000,000 years or 2, and then they go. So obviously, with the great span of geological time, it's probably true that the majority of species are extinct. And I think we know also from the fossil record and other studies that species can either go extinct absolutely, they entirely disappear, or they can evolve into another species. We also know, of course, from long study of the geological record, that there have been many times of extinction, not just the end Cretaceous, which is the one most people are familiar with, the loss of the dinosaurs and the ammonites. But of course, when we look at a graph like this one, which shows us the last 600 million years of the Phanerozoic, essentially, and the y-axis is showing the percentage of extinction, the percentage of the living biodiversity that was disappearing at that time. You can see, of course, there are many, many peaks of extinction, some of which we discriminate as, the big 5, highlighted with the red arrows. But you can see there are many other extinction events as well. So I'm just going to try and do my can I do a laser pointer here? Not sure. No, I won't try that. And so we know that there were events in the late Cambrian that are not normally called mass extinctions, but were quite severe. There are lots of others through the Paleozoic. There's this one here in the Carnian. There are various oceanoxic events in the Jurassic and Cretaceous, and similarly the PETM in the Cenozoic. So there are many, many kinds of extinction events. Oh, here we go. But don't we need a time machine to see them? So I'm going to show you 2 examples of recent research on the extinction at the end of the Cretaceous, just to show you how it's possible that you'll be familiar with some of this, I expect, but just to put this in a clear way that we can explain to non-geologists and say, well, actually, we can test certain things about these ancient events. Oops, here we go. And so, of course, the image of the end Cretaceous mass extinction shown here of the dinosaur and the meteorite, it packs it all into one image, the subjects that everybody is fascinated by. And of course, it's important to remember, if anybody asks you, well, what's the use of geology or what's the use of paleontology? Well, if we didn't have those subjects, we wouldn't know about mass extinctions or about dinosaurs. You cannot predict them from life today. I think most of you will know the background to the evidence for impact at the end of the Cretaceous, so I'm not going to linger over this part. Just to recall that it was in 1980 that Alvarez, father and son, together with some colleagues, proposed the idea, based on this evidence, that there had been a large impact of an asteroid, a giant meteorite, at the end of the Cretaceous. And it was based on the observation of a peak in iridium. And recall that iridium is a metallic element that is not generally found on the surface of the Earth. And normally any iridium we do find on the surface is assumed to have arrived from outer space on tektites and other small meteorites. So they interpreted, not unreasonably, this peak at the KPG boundary as evidence for a big impact. Oops, wrong way. And they proposed a formula which enabled them to back calculate the size of the meteorite, the size of the asteroid, based on an assumption that to kill things, you had to encircle the globe with dust. At the top of the atmosphere, you had to have enough dust that it would black out the sun and prevent photosynthesis and produce cooling. And so it's possible to work out the area of that sphere that encloses the atmosphere at that appropriate level. And if you suggest that that dust layer has to be whatever, a centimeter or half a centimeter thick, you can then calculate exactly the volume of dust that you require. And then working backward from that, it's possible to work out the size of the crater that would produce that amount of dust, bearing in mind that a lot of the stuff that comes out of the crater is not going to be dust grade, it's going to be larger stuff that falls back. And then back calculating when you have the crater size gives you the size of the meteorite. And so this is how they did it. And you think, my goodness, that's pretty smart if it's true. And we teach this to the students and they can do the calculation themselves. And then since 1980, I think many of you are aware that whereas Alvarez and colleagues only reported the iridium anomaly at 2 locations, one in Italy, one in Denmark, since then the iridium anomaly has been identified in hundreds of localities, everywhere you look pretty much, as well as a whole lot of other phenomena that indicate support for the idea of an impact. But the big question is, did this kill the dinosaurs? Did this kill the ammonites? Here is the crater. So one of the criticisms at first was, we don't have a crater, therefore we don't believe you. Of course, Alvarez and colleagues were right in everything they said, which makes their achievement all the greater because, of course, they did it with modest amounts of evidence, but they were bold, which is a good thing. And subsequently, I'm sure many of you know the story, the crater was located in the Yucatan Peninsula of Mexico. And in the late Cretaceous, the impact was entirely on the oceanic shelf, in shallow marine water. Sea level, of course, was much higher because of the mid-Cretaceous rise in the amount of mid-ocean ridge activity, raising sea levels by maybe 200 meters above where they are today. And hence, of course, the Cretaceous coastline is rather different from today's. And so here's the impact. And it has been mapped, of course, by using geophysical methods because it's buried under younger sediment. So all of that is now well known. However, there was still an open question as to whether the impact caused all of the extinctions at the end of the Cretaceous, or could it have been the Deccan Traps? Again, I think most of you will be aware of these, that amongst the many large igneous provinces in the history of the Earth, including the Siberian traps, which we'll come back to in a moment, which are responsible for perhaps for the end Permian extinction. The Deccan Traps are here, and they resulted from the passage of India, which of course was an island at the end of the Cretaceous, across the Seychelles hotspot located about here, and moving north, and a track of igneous material, basalt, and today covering a very large area of India. And this is what the scenery looks like, layered basalt. and huge volumes and production of greenhouse gases and all the other things. So how could we determine the relative roles of impact and volcanic activity? Because they're both going on at the right time. The evidence for dating, of course, of the impact is that it happened bang on the Cretaceous Paleogene boundary, based on radioisotopic dating of melt rocks at the bottom of the crater. So that's contemporary with the impact. But what about the Deccan Traps? The dating of these volcanic layers suggests that volcanic activity kicked off before the end of the Cretaceous and carried on fitfully, sporadically across the KPG boundary into the beginning of the Paleogene. And of course, later we will see, and I think many of you know, that hyperthermal events driven by large igneous province volcanic activity have actually caused a lot of extinctions. So why not this one? So it's a very valid expectation. So the important point to bear in mind in terms of testing between them is twofold. Number one, we should find a peak in activity occurring bang on the KPG boundary, because that's when the extinction happened. The two events have to coincide. And secondly, we have to see whether there is a cooling or a warming associated with that activity. So remember that the impact must cause cooling, because the whole theory is that the impact blacks out the sun and stops the rays of the sun reaching the surface of the Earth. So even for a relatively short amount of time, maybe even as little as a year or tens of years, you should have cooling. Whereas in the case of volcanic eruption, because the killer is the cocktail of greenhouse gases that emerge from the volcano, therefore you should have warming, maybe over a somewhat longer span of time, but nonetheless cooling versus warming. So the test was done in the year 2020 by this person here. This is Shelley Hull, who's a professor at Yale University, and she and a team of researchers decided to tackle this. And the time was right, because the quality of radioisotopic dating is now good enough that you can discriminate spans of time in the tens and hundreds of thousands of years, not millions, but tens and hundreds of thousands. So in this diagram at the top right, the time scale is in fractions of a million years. So 0.2 is 200,000, 400,000. So 0 is the KPG boundary highlighted in red. And counting back, we have 200,000, 400,000. Counting forward, we have 200, 400, 600, and so on. So the time scale is pretty good. And then secondly, what they're showing here is the temperature based upon oxygen isotope measurements, primarily from the skeletons of foraminifera and other planktonic organisms. So what Hull and colleagues did was to choose the very best isotopic data they could get. Huge amounts had been published, and they wanted to use only those values that were well enough dated that they could be fit to the time scale. So a lot of the older measurements wouldn't do because they were not very well dated. And secondly, they had to be measured according to the current criteria. So the formula that allows you to convert the ratio measurement, the oxygen isotope measurement, the ratio between oxygen 18 and oxygen 16 as a measure of temperature, they had to choose those values. All the different colors then indicate they're measured from different sources. There are some terrestrial ones from leaves and soils. Others are from marine organisms, but they have to be on the surface of the ocean, not in the deep ocean. What do they find? They find the average value shows a peak of temperature about 200,000 years before the end of the Cretaceous. Then the temperature declines. There's quite a sharp dip, a V at the KPG boundary itself, and then it bounces off, rising slightly into the Paleogene. So QED, they have answered the question. It was the impact. That's the end of the story. And that is a test. I shouldn't say it's the end of the story, because they might have made mistakes. And so clearly every aspect should be tested and checked. but they have produced a convincing test of the hypothesis. What they're now showing is very clearly that the Deccan Traps were erupting at peak 200,000 years before the end of the Cretaceous. They may have had effects on the weather and on life, but not marked effects. The actual extinctions happened at the KPG boundary in coincidence with the impact of the asteroid. So that's pretty cool. You don't need a time machine. This is a case of offering a testable hypothesis, providing the evidence in great detail. And if some critic would come along and say, well, I don't like it, I think the Deccan Traps are still the main cause, you would have to say, okay, look at this diagram here. Could you please improve upon it? Could you please find additional and better quality data at this level of analysis that will make your point? Because otherwise this would stand perhaps as the best presentation at the moment. What about the other test I was going to mention? I should have trailed this. It's been suggested for quite a long time that the asteroid hit the Earth in early June. And again, some of you will know the story, and some of you perhaps not. But it's a really nice, just like the previous one, just like this one too. They're really nice examples where you can show people, if anybody is unsure, you know, what's geology for? What can you achieve? It's all happening in the past, so we don't really, it's all guesswork. That's the main criticism we face. Oh, it's all guesswork. And you say, well, not at all. There are cases where it's not guesswork. We present the data, we can read a lot from it. So some of you will have seen this there's a David Attenborough program probably 2 or 3 years ago called The Last Day of the Dinosaurs, and that told the story, and is based around fossils like the one shown here at the top. I'll explain what the fossils are in a moment. These are fossil bones. You can see some teeth and so on. We're focusing at first on these little yellow blobs. So this is a 3D image of some fossils and their associated bits and bobs. And the yellow things are impact spherules. So these are glassy spherules that are related to the Chicxulub impact. They are here found in Dakota, which is about 2,000 kilometers away from the impact site, but that's fine. With an impact of this size, we would expect some of the ejecta to fly many thousands of kilometers before it lands. These are melt products that are produced by the enormous energy of the impact and of the backblast as the Earth's crust recovers from this huge impulse of energy. And the rock that is hit melts. The chemistry of these spherules is not igneous. The chemistry is a mix of limestone and sedimentary evaporite, which is not a normal kind of chemistry for a volcanic melt product. And so these are confidently linked with the Chicxulub impact. If so, then this fossil creature, and I'll tell you now, these are the gill arches in the neck region of a very large fish. And so the argument is that these fishes were swimming around in shallow water in what is now North Dakota, and they died, being killed by the blast or the heat blast or whatever was coming. And the bead-like spherules are settling in amongst the carcasses, even within the gill skeleton. Maybe they're even breathing them in as the patter of little glassy beads falls on the lake. They might even be sucking them in unwittingly into their gill area. So it's a bit of a long-winded explanation, but that's what the claim is, which has yet to be fully tested, but of course can be. And so let's have a look at these structures. These then are the gill arches. These are the skeleton. Oh dear, what's going on here? The skeleton behind the head. These are in paddlefish and sturgeons, which existed then at the end of the Cretaceous. They exist today. So that's quite helpful. You can make the connection. You can study the bone of modern ones and compare them with the fossils. So what we're looking at the bottom here, if we look at figure D first, where it says death of fish, that's the outer part of one of these bony rods. And the bony rods shown above are more or less circular in cross-section, and the outside then is convex, and the middle is at the bottom. And so the growth lines highlighted with red arrows are shown here, 1, 2, 3, 4, 5, 6. It's well known from the modern paddlefish and sturgeons, and indeed a lot of other fishes. They're cold-blooded. They tend to grow in summer, and they don't grow much in winter. It depends on the amount of food supply. It depends on the temperature. When they're not growing very fast, the bone cells are quite tightly packed and they look dark. When they're growing fast in the summer, the bone opens up and it looks quite pale. So what can we see here? The fish was 6 years old when it died. Well, that's neither here nor there, really. But when we look at the last winter line at the top here, there's quite an amount of pale-colored bone above. So now I think you can see if winter in Dakota in the end Cretaceous ended, say, in March, then we've got growth for April, May, maybe a bit of June. There you are. It's not just this one specimen. Melanie During, who did this work, she's a PhD student. She repeated it, and other teams have repeated it on other fish. And it doesn't matter whether the fish is 6 years old or 5 or 7 or 2. It's this increment of growth after the last winter dark line. And the other analyses here are fluorescent images, petrological thin sections, X-ray thin sections. And on the left here, A is isotope measurements, carbon isotope measurements in this case, showing variation in the carbon content incorporated into the bone, corresponding to the winter-summer cycle, confirming it. So there we go. It happened in June. And people did similar analyses ages ago looking at fossil lilies, which had been frozen. And again, you predict they'd be freezing because, of course, you get a snap freezing episode shortly after the impact. And again, lo and behold, those lilies had frozen in the floral condition. The flowers were just opening that they would have had in early June. So there's double corroboration there. So that's pretty good if you want a story to tell, to explain a little bit about what types of research people are doing and the unexpected facts. So we know its impact and that the volcanic eruptions had a minor role. And secondly, we know the impact happened in June. I'm just going to say a very brief word about extinction today, because for many people, this would be the connection where they might be interested to know, what do we learn about extinction in the past that would help us to understand extinction in the future, let's say. So there are many studies like this one where people have looked at the threats to wildlife, and a lot of it is to do with exploitation. That's like fishing and cutting down forests and so on. Habitat degradation, that's where seas and forests and so on are modified for human activity and limiting the opportunities for wildlife. We also have images to remind us about the wonderful pesticide DDT. It seemed too good to be true, and indeed it was, because not only was it killing the pests, it was killing everything, including human beings. Also shown here is the great auk, one example of a species that probably humans did drive to extinction. And so in order to understand something about extinction today and how we can compare it with extinction in the past, we need to know what is the diversity of life on Earth today. And it's not so easy to establish. And again, this is worth knowing, that whereas at the present day we can have access to total knowledge, because we know, of course, a lot of the data in the past is masked, is lost. We know that we're looking at limited amounts of data when we look at the geological past. But actually, in the present day, we still lack a lot of knowledge. But nonetheless, I think a useful figure, just a handy number, if you want one, for how many species are there on Earth today, it's generally agreed to be about 10 million. So 10 million species. And what about the amount of extinction? So, of course, we can document a lot of historical extinctions. We've seen the great auk, that was 18 something or other. We know about the dodo, that was driven to extinction in 16 something or other. And so, of course, we can add all of these up. We have some historical records. And according to this review about 10 years ago, Monastersky in Nature, he came up with something like 765 historically documented extinctions, which can then give you some information to plot rates of extinction through time. But of course, that historical data is very limited because it is only birds and mammals and trees and so on. We've got no idea about the actual rates of extinction of insects and microbes and fishes and groups that people are not kind of watching all the time. But nonetheless, we can use that kind of information to begin to calculate measures of extinction. And they can give a measure that's actually pretty high, something like 80 species per day, 78 in fact, has been quoted. That's at the top end. That's quite a high-end measure, which, you know, you might think, oh, we've got 10 million species, we can afford to lose 80 per day. That's probably okay. But actually not, you know, that is a very high rate of loss. And again, according to Monastersky, that kind of figure, 80 per day, 690 per week, as shown here, is definitely at the high end of the estimates. And at the low end of the estimates is something like 10 extinctions per week, which doesn't sound too bad when you remember this is across everything. Birds, mammals, flowers, ferns, insects, mollusks, everything. Is that unusually high? Are these figures more than we would expect normally? So we can make a quick rule of thumb guess of what the extinction rate ought to be if nothing else was happening. If there are 10 million species on the Earth, and if they each last for about 1 million years, then we would expect something like 10 extinctions per year. That's a pretty simple calculation. That's a useful figure. And so 10 per week is 50 times too high. And that's the lowest end estimate, of course. This is the most, 10 a week is the most optimistic estimate of current rates of extinction. But you might be surprised then by that range. It's anything from 10 to 700 extinctions per week. And at the moment, nobody quite knows for sure where it falls. We'll just keep that in mind. What can we do about it? Well, if we want to, we could try and bring all of these ancient species back to life. And some of you may have read about the efforts to bring the mammoth back to life by genetic engineering. And this is, do look it up later if you've not heard of this. There's a big company in Texas called the Colossal Company. And they are the de-extinction company. They are, they claim, bringing the mammoth back to life. On behalf of humanity, the animal kingdom, and the universe, we accept the challenge. So no false modesty there. But I'm not going to talk any more about that. I'm going to talk more about the geological record. So we've looked a little bit at the end Cretaceous extinction. I think most of you will know that the end Permian mass extinction was much, much bigger. And so I ought to have a look at that briefly. It's one of the ones I've studied as well myself. And so we can look at these extinction events in different ways. We can look at them qualitatively or quantitatively. So, of course, a qualitative look at the end Cretaceous extinction event would show you something like, before the event, you'd have a landscape full of dinosaurs and pterosaurs in the oceans. The scene would be full of plesiosaurs and mosasaurs and ammonites and belemnites and blah-de-blah-de-blah. And then after the event, all of those things would have gone. And on land, you would see mammals and birds and lizards. And in the oceans, you would see, well, typical modern fishes and shellfish and so on, but no ammonites and so on. Here, the qualitative look at the ocean floor, shown in these classic kinds of block diagrams that some of you will be familiar with from Stuart McKerrow's book from 1968, where he had these lovely, lovely block diagrams. At the very end of the Permian, you might see, for example, a reef like this, full of dozens and dozens of species, with all sorts of other species living in and around and above the reef. And in fact, the sediment below is a bioclastic limestone. So the whole structure here is very rich in life. And there are burrowers and all kinds of creatures living within the sediment also. After the event, it's a very anoxic looking scene. The sediment is dark colored, black or dark gray. Oops, wrong one. And there is no sign of any burrowing. There are very few fossils. It's not bioclastic at all. And there's just a limited array of organisms like Lingula, the brachiopod, these paper pectens, keeps jumping around, these paper pectens like Claraya. Quantitatively shown here, this is from South China. The data show us actually that there were, oops, sorry about this, seems to be hopping around all the way. There were two extinctions, one at the end of the Permian, very end of the Permian, the next one at the beginning of the Triassic, and they are separated by something like 50 or 60,000 years. So this again is a big eye-opener for me and for most people who were brought up learning about radioisotopic dating and the kinds of error bars. Now it's possible to, in combination with astrochronology, tuning the Milankovitch cycles in sedimentary piles and so on, to get the precision of dating right down here to maybe 50 or 60,000. And of course, we can see at these levels there is enhanced extinction. And it totals up to something like 90 or 95% of species disappear. On land, it's the same. You go from a very rich fauna here on the right at the end of the Permian. This is the Viatkian fauna in Russia, which is very well known. And there are similar well-studied faunas, for example, in the Karoo Basin in South Africa. And then famously in the earliest Triassic, virtually all you see is Lystrosaurus. And you lose a lot of the diversity, the complexity of the ecosystem. Most of these species have simply gone, and life is knocked back substantially. So just a little side look at some field work in Russia. In happier days, we went to Russia every year and did a number of expeditions. As you can see, the dates are there. And we were studying the terrestrial Permian Triassic, looking at the terrestrial PT boundary. And if you look at this geological map at the bottom, just to orient you, north, south, east, west, this is Moscow. And the scale bar, you'll notice, like everything in Russia, is huge. This is 1,000 kilometers. So from Moscow across to the Ural Mountains is 1,000 kilometers. We went to locations all over here, down around Orenburg and up the Ural chain. And everywhere you're looking, the Permian, I should say, is pink. The Triassic is blue. So there are loads and loads of locations where you can see the contact. Oops. And so this is what it looks like. And we were told by the Russians, the lower parts are Permian, soft sediments slowly accumulating. And this sudden crag of breccia conglomerate is the earliest Triassic. And looked at more closely, here is Richard Twitchett, formerly of University of Plymouth, now at the Natural History Museum. And this is Andy Newell, who has just retired from the BGS, peering in, and here is the boundary. The Permian at the bottom is relatively fine-grained river and lake sediment, and then above you can see this conglomerate with great chunks of older rock coming down from the Ural Mountains. So what does it all mean? The Russians told us this was because of renewed mountain uplift, that the Urals were reactivated, they were beginning to rise a little bit more, there was some sort of tectonic activity going on, which if it was true could then lead to steepening and greater erosion. But then when we discussed it with them and reminded them that you see the same thing in South Africa, in India, in Spain, other parts of Europe, they realized this was something global. This is probably not just a local tectonic thing. So the second thought was, could it be increased rainfall? Because of course, if you go from low energy to high energy, from, as shown in these block diagrams, from meandering streams to braided streams, of course, this represents a sudden increase in energy, great alluvial fans of sediment coming, dumping off the Urals. It could be increased rainfall. But in fact, that's not the case, because all of the sedimentary successions show that aridity was increasing across the PT boundary. So the third possibility, and the one we think is probably correct, is loss of vegetation. And that was predicted already, because various geologists had already identified something that they called the coal gap. And so across the Permian Triassic boundary, there seemed to be a loss of coals. And we're not used to the idea of commercially exploited coal of late Permian age, but this is commonly the case, certainly in Asia, definitely in China, because a lot of their usable coal is actually that age, latest Permian. And then there's a gap of about 10 million years through the early and middle Triassic with just no coal anywhere. And that corresponds to a loss of forests, a loss of trees. So even though a lot of species of plants didn't die out in a huge way, nonetheless, there was an enormous hit on the landscape. And so what's going on here? Can we somehow understand all of this? It suggests that there was acid rain or something happening. And the forests were being killed, and there's additional evidence that the trees and the soil were all being washed into the ocean. And so this suggests some hugely catastrophic thing happening on land, stripping the landscape, essentially turning the surface of the earth, the landscape, into rocky surfaces with very few plants, just low bushy plants. And of course, that would limit the amount of animal life that you could have. So how does all this tie together? Most of the explanations then take it back to the Siberian traps, which, like the Deccan traps spanning the KPG, without a doubt, the Siberian traps span the end of the Permian and into the early Triassic. And you might think we would reject this and say, no, it's impact. But in this case, there is no evidence of impact anywhere. And in fact, the Siberian traps, for whatever reason, are widely accepted as the smoking gun, as the trigger that set it all in action. And so here's a very famous diagram that some of you may have seen. It's in various books by Paul Wignall and various articles that he's written, currently at the University of Leeds, and many others have added to this. And the work we have done on the terrestrial situation is part of the story. So here I've highlighted the things that are happening on land in green, the things that are happening in the oceans in blue. And so it all starts with the Siberian traps eruptions. They produce a bunch of gases, of which carbon dioxide and methane are greenhouse gases. And SO2 is rapidly released and rapidly absorbed by the atmosphere, has a cooling effect. But in particular, when SO2, of course, mixes with water in the atmosphere, it produces sulfuric acid. So it is the dominant producer of the acid rain that led to increased soil erosion, increased weathering, and indeed the killing of the plants, disturbed landscapes. All these kinds of things are happening largely because of the acid rain, but also because of warming. And then the warming in particular has a catastrophic effect on life in the oceans, because as you turn the temperature up and up and up, life in the tropics, both on land and in the sea, just cannot survive. And it has to move away. And the effects of the warming are a coupling of increased marine productivity. You get a kind of plankton bloom, and this is fueled by the increased weathering and the wash of ions into the ocean, somewhat analogous to the poisoning of lakes by excessive nutrients today. Phosphates and nitrogen and so on from fertilizers can produce abnormal swamping of a lake or a shallow sea by rapid growth of life and then a total collapse. And in the case of these events, at the end of the Permian and others, collapse of the system in the ocean and the heating of the surface water leads to perturbation of the position of the thermocline. It breaks the normal cycling of water from the deep ocean to the surface and back to the bottom. So there's no longer a transport of oxygen to the seabed. And indeed, some of you who've heard talks by Paul Wignall, for example, will be very aware that he's studied a great deal the subject of anoxia. So nearly all the sediments in the earliest Triassic, as I showed a moment ago, are anoxic, no life on the seabed. And so all of that then weaves together. And that is the widely accepted model. And I think just as a preview, this is also the model, as Paul Wignall and others have pointed out, this is also the model that probably applies to lots of other extinction events, maybe most of them, except for the end Cretaceous. So what else do we know? If we look at the diagram at the top right, first of all, here's the Permian Triassic boundary in red, and then we've got the early Triassic and the middle Triassic. And Joachimski and others have done a lot of study of the oxygen and carbon isotopes, and they report, of course, peaks in both at the PT boundary, and that's the driver of the extinction. But they note also there are peaks in these values later in the early Triassic. Here's one about 1 million years later. Here's another and another. So at least 2 or 3 in the early Triassic. Caused maybe by additional volcanism. It's not entirely sure whether it's continuing Siberian Traps volcanism. Probably it's contributed from other volcanic activity. And so a consequence of this heating of the atmosphere and of the seawater, the surface water, perhaps is a driving of life away from the equator. And so a Chinese geologist, Sun, noted in 2012 with colleagues that there is a so-called tropical dead zone. And the tropical dead zone extends over much of the tropical area. It's a bit asymmetric, but both in the oceans and on land, we seem to find that life has disappeared. And so that's consonant with the model. So recovery, of course, is important. I'll skip through this fairly quickly because, of course, we know in the case of all of these famous mass extinctions that obviously life bounces back, and it often bounces back in a very different form. So the end Permian extinction event was the biggest of all, and the recovery actually marked the biggest difference between the before and the after. You go from the Paleozoic type faunas to the Mesozoic type, which are often called more or less modern, because in the oceans, these are dominated by modern groups, not the brachiopods, not the trilobites, not the graptolites, but more modern type bivalves and gastropods, crustaceans, teleos type fishes. So all the key groups, echinoderms and so on, are the ones that we see in the ocean today. And there's a great deal of knowledge has been gained about these, a lot of it from China. So here's an example of the explosion of different groups of fishes in the Triassic. We can look at plant evolution, although it was sort of gradual. Nonetheless, the PT boundary marks a switch from floras dominated by ferns and lycopods to conifers and cycads. And in the oceans in general, you go, if you remember the work of Jack Sepkoski, you go from the Paleozoic type faunas in red to the modern type faunas in green, if you compare the distributions of fossils between the two. There have been other smaller events. I'm just going to touch on this particular one just as an example, one of many. This is the Toarcian ocean anoxic event 183 million years ago. It corresponds to the jet rock at Whitby. It corresponds to the Posidonian Schiefer in Germany, sampled around Holzmaden. And it corresponds to a locality called, with the lovely name of Strawberry Bank in Somerset, in Ilminster. And this is something that we have been working on because it's kind of local to Bristol. And thanks to the work of Charles Moore, one of these wonderful, high-achieving Victorian geologists who did all sorts of wonderful things, he made large collections from this locality in his own hometown, and the collections are to be seen in the museum in Bath. And this is what they look like. This is the head of a very large fish. That's a 5-centimeter scale bar. And the lovely thing is these are 3-dimensional. And you can, he had them prepared in great detail like this. And there's a list of the numbers of specimens, hundreds of insects and various marine creatures. There are about 100 of these large fish. They're about 1 meter in length. They can be CT scanned to give you a lot of detail inside. Here are some of the insects that are trapped within the marine sediments. Here are some fossil crocodiles and other fishes, ichthyosaurs. And as I say, the CT scanning is fantastic. We've had a lot of student projects like this one where the student work, oh, I can actually make this work, where the student we take X-ray scans and the student puts it all together, and look at all that detail. And if you tried to do that with some of Mary Anning's lovely ichthyosaurs from Lyme Regis, you'd get nowhere, because they are actually preserved flat, whereas this is evidently in 3 dimensions. Here's the reconstruction. We maybe put it a wee bit inshore, maybe it's a little bit further offshore. And it's a curious situation because this is a case of exceptional preservation, 3 dimensions, soft tissues, insects, where we get the insect kill associated with the marine life kill. And I keep suggesting things which nobody denies, but we can't quite prove it, which is it's well accepted that this ocean anoxic event is not only anoxic, but is also euxinic. And so if you know about Euxinia with an X, this is the status of the Black Sea, which is where it's named from. And these are situations where the amount of sulfur in the oceans is excessive. And you get a tremendous separation of the deeper, colder water full of sulfur and anoxia that is incapable of supporting life, but has a tremendous ability to preserve fossils because there are no scavengers. It's anoxic. And the surface waters, so in the Black Sea, you'll know some of the story, I'm sure, of the warmer surface waters passing out through the straits of the Bosporus and the deeper sulfur-rich waters at the bottom. And so the suggestion is that the sulfur on occasion may leak right up to the surface, and all that warmer surface water is driven away. And you have leaking of sulfur into the atmosphere above, which could then be killing insects and anything flying over. And they would all just, unusually then, just at these points, you get dead insects falling in. And it's odd that all of these locations, and there's another locality in Canada, I think, that have this exceptional preservation coinciding with this ocean anoxic event. And the Toarcian ocean anoxic event then was actually driven by volcanic eruptions in South Africa, the Drakensberg volcanics. And the model for the extinction is exactly the same as for the end Permian. The volcanics drive global warming and acid rain, and in this case, coupled with Euxinia as well, leading to a great deal of killing. So put this all together, it seems that now we're realizing increasingly that a lot of these events in the past are hyperthermal. So you see the word there, hyperthermal means high temperature. And all the events indicated with a red arrow, they're slightly offset. It just jumped. Here's the end Permian, here's the Toarcian, and all these others, except for the end Triassic, where I've drawn a little meteorite. At least 10 or 12 other events seem to be hyperthermals. The latest of which is the PETM about 50 million years ago, when there was another phase of warming associated with extinction, but not massive extinction. This is not one of the big 5. Here's a very, graphic image showing the hyperthermal model, highlighting the eruption and focusing on the gases. We're not really saying anything about the lava because that's just a local thing. We're looking at it on a global scale, and you can see here the plant death and the major soil erosion, the washing of soil into the ocean, leading to extinction. So my last theme, I think, is how does this kill? Because we can sort of think of a catastrophe arising from an impact, but what about just gradually warming things up? Well, it does kill. It doesn't necessarily kill immediately. And of course, plants and animals are capable of movement. So the sharpest effects would be at the equator, where surface waters like today might be 25 or 30 degrees C. And a lot of life, including humans, are fine. You know, we can cope with that. 25 or 30 is a nice day on the beach. But if you raise the temperature by 5, 10, 15 degrees, as happened at the end of the Permian, you're up into the 40s. And I think you know that becomes intolerable. And what do organisms do? They don't just sit and swelter, they move, they get away. And yet that then can have a massive killing effect, because remember that as today, probably also in the past, the areas on Earth with the highest biodiversity would be the tropics. We think today of tropical rainforests, we think today of coral reefs, but their equivalents in the past would have been the sites of highest biodiversity. So if you heat up the surface oceans and you progressively cause the tropical organisms to move away to the north and the south, they will surely come into competition with the organisms that are already there, or which will be themselves moving on because their happy climate belt is moving away. So they're all on the move, and eventually they get too far, they fall off the edge. So it seems this is enough to cause extinction. The amount of extinction depends to some extent on the scale of the volcanic eruptions, and in turn they determine how many degrees C the temperature goes up. So at the PETM it's maybe 3 or 4 degrees. At the end Cretaceous it's maybe 10 or 12 degrees. So now as geologists we actually have a shopping list of events of different magnitude. So how do these kill? These are the kinds of consequences of high temperature. So there's global warming and heat stress. Hypoxia means low oxygen levels. So that when temperatures go up, you increase the oxygen stress on organisms. Hypercapnia is a fancy word for excessive acidity in the ocean. And we know that acidity will kill because it dissolves the carbonate skeletons of lots of organisms. Aridity on land, of course, lack of water. Acid rain and mass wasting, that's the rain and the removal of soils into the oceans. And wildfires, although they in themselves, although dramatic on the day, are probably not causing much trouble. And there are intersecting effects. There's a lot of study of the effects of heat. And as organisms get hotter, I've got a sweating pig here, they need more oxygen and they lose water. And so all of these effects interact. So these are the various killers that are caused by the hyperthermals. And these are probably common to the majority of these extinction events. And so I can wrap up now. The key messages from my talk are that a huge amount has happened in the last 30 years of research, and I think a lot of you will be aware of some of this. And I've given you some examples of current ideas, and there's still so much more to be done. This knowledge number 2 very directly informs our understanding of modern extinction. I think it's important that we, as geologists, will always have a view to what people care about. Many members of the public maybe don't care about rocks and fossils, but they will care about the future of the Earth and those kinds of questions. And we can make a very clear statement, I think, that we have information of value. And bear in mind that I mentioned there are maybe 10 or 12 hyperthermal events in the past, and they're organized in a scale of amount of temperature rise from 2 or 3 degrees to maybe 10 or 15. And so we're talking about today, there's maybe been a degree and a half rise in temperature. We are seeing some of the consequences. If somebody were to say, well, what happens if we go up to 2 degrees or 3 degrees above normal? We can say, yes, well, we have some examples in the past that we could look at. And if somebody says, well, what about 10 degrees? Well, yeah, we have some examples we could look at. Number 3, of course, we mustn't be full of doom and gloom, of course. Mass extinctions in the history of life have enabled important changes to happen, which otherwise might not have happened. And I think the universal hyperthermal model, which a number of people in the field have noted, is a new idea. And I think it's gaining ground. It seems to make sense. The more we look at these events of different sizes, the more similarities we see. So if you're interested in these stories, this is all in the book, what I've talked about this evening, plus lots more. There are 15 chapters. I've given you the meat of maybe 2 or 3 of those chapters. I've tried to represent in a readable way in a fun way what we currently know, but also how we know it. It's not just declaring this, this, this. It's actually saying, well, this is how people are studying it. These are the kinds of evidence we have, and some unexpected sidelights and some pointers to the future, perhaps. So I think I'll stop there, and I'll stop sharing my slides, and I'll do my best to answer any questions people might have. Thank you for your attention.
Absolutely great. Thank you, Mike.
Yes, pleasure. At the moment is that it did not, but of course we would expect that it would have caused some extinction. And I think what's needed is some more detailed study of the last 200,000 years of the Cretaceous to really pick apart in detail what was going on just before the impact happened. And that kind of work hasn't yet been done, because I think in most places people have not been able to revise the timescales to the new level of precision, or new level of precision. So this is a very open field for any enthusiastic person to pursue.
Okay. Plenty more work for you and your colleagues, in other words.
So yes, the survivors. I think in some cases, so people have always wanted to know this, is there selectivity? Can you in some way say that the victims share certain features as the survivors? And certainly at the end of the Cretaceous, you're right, things like crocodiles, turtles, mammals, lizards all survived. And there is no doubt they're small and the dinosaurs are big. But the trouble is there are a lot of little dinosaurs, and they also disappeared. So it's not quite as simple as we might think. And then others suggested maybe the crocodiles and the turtles were living in lakes. And that's true. And could they duck under the water and somehow preserve themselves? To an extent, but that doesn't necessarily explain the birds and the mammals and the foraminifera and the bivalves and the gastropods. So it's difficult to find a universal feature across everything. But I think where people have looked at more restricted groups and said, okay, let's look at the mollusks, or let's look at the fishes. Which are the ones that survive? So the best characteristics for ensuring survival, number one, be cosmopolitan, i.e. live all over the earth. Number two, don't be too big. So humans are probably a bit on the big side, whereas rats and cockroaches are a better size for survival. Number three would be don't have a very specialist diet. So we're okay there. Humans will eat almost anything. Pandas, not good. Elephants, not good. And that's about it. It's been very difficult to find any other characteristics. And those are ones you might have predicted, you know, to be a generalist, to be not very big, to be geographically very widespread. And beyond that, all we can do is just report. You know, it's difficult to find the reasons. We can simply report. These are what survived, these are what did not. Part of it, I think, the final thing I'll say is part of it is probably what David Rauch, the great American paleontologist, called the field of bullets. And he had in mind the First World War, where, of course, you could have in your battalion, half the men could have been very well fed, very strong, very well exercised, highly intelligent, highly trained. The other half could be very poorly fed, hungry, small, not very strong, stupid, poorly trained. You all jump over the parapet and run towards the enemy. Who's going to survive? It's the field of bullets. There is nothing predictable. So in some of the events like the end Permian, perhaps it was so severe that it may be difficult in the end to find adaptive reasons why certain things survived. It may just be, in many cases, good luck. And so it's important to think about those two aspects, I think. Yes. So the answer is mainly not. So I think you know during the Pleistocene, there were many glacials and interglacials. The ice sheets in the north expanded and retracted, expanded again, retreated. And to a large extent, life just went back and forwards. And so for much of the late Pliocene and Pleistocene, when the climate was going between these cool conditions, you were not causing extinction because, of course, animals and plants can move. And you may not think plants can, but of course, over a matter of hundreds or thousands of years, the seed are being thrown in all directions, but of course, they will establish themselves where they can. And it was only at the very end, I think, that the large mammals disappeared, like the mammoths and woolly rhinos and such like. So we see it as important because we're mammals and we can identify these species. But actually, it's not really an extinction event overall because it was only those large mammals that disappeared. And it's a very similar reason to the hyperthermals, whether it's cold or hot, it doesn't matter really. The organisms can move, but they have to sit where they are comfortable. So you probably know that over England at certain points when the ice sheet was expanded, you would have had mammoths and Neanderthals. And then when the ice sheet disappeared, we even had hippopotamuses and African type elephants living in London. So, you know, that these movements were quite substantial, the whole depth of Europe pretty much. And yet in the end, it was a fairly modest extinction event, really.
Yes, thank you.
Yes.
Oh, yeah.
That's a great question. I think that she obviously attacked the easiest one. I think this is one thing you quickly learn as a geologist, that the quality of data is better the nearer you get to the present. So of the big 5 mass extinctions, you better look at the end Cretaceous because it's the most recent one. And there, the quality of data really is very good. I don't think we could quite do that quality worldwide for the end Triassic or the end Permian event yet, but I suspect, you know, people will be looking at it. We've got a couple of ocean anoxic events in the Cretaceous. There is the Toarcian event. So I think lots of people are looking at doing that kind of study, absolutely. And I think that couples back to the first question about the decline and who survives and who doesn't and the timing. There's just so much more yet to be done. And I think it's an exciting time. We're sort of seeing a really major step change in the quality of the dating, which will enable lots of these questions to be answered. Yes, great question. Great question. I think many of you will know a lot more than I do about meteorite geology. During the Phanerozoic, there were many meteorite, asteroid hits on the Earth. A fair number of them were as big as the Chicxulubs. There are other craters, the Manicouagan crater in the late Triassic in Canada, and a number of others which have these 100-kilometer plus craters. Why this one? Everybody says it's because a lot of the others hit inert, older shield rocks, and so Precambrian and so on. So the Manicouagan hits Precambrian, nothing much happens. The dust, yeah, blah, blah, blah. But this Chicxulub impact was in the shallow sea, and it hit limestone and evaporites. It's estimated that a huge amount of sulfur was released into the atmosphere at the time of that impact. And so I think you're right, spot on. This is what people say, people who study meteorites, people like Jay Melosh, that of the many big impacts, this was the killer because unusually it hit fresh sediment and with a lot of sulfur, and that sulfur in the atmosphere then had pretty catastrophic killing effects. Yes, so the late Ordovician mass extinction is, of course, the first of the big 5. You're absolutely right. It's on a magnitude with the end Cretaceous, the end Triassic. I think for the moment, people are not so sure about the cause. It's always linked to the buildup of the ice cap in Antarctica, and that coupled with that, sea levels fell dramatically, exposing a huge amount of the shelf, and so the bottom of the ocean was exposed, and there's a great deal of change in the weathering rate and transport of minerals into the oceans. But it seems to be primarily, there's no evidence for either an impact or major volcanic eruption at that time, as far as I'm aware. And so it's a very different kind of model. I talk about it in the book, but forgive me, I didn't talk about it in the lecture tonight. I just wanted to focus on 2 or 3 examples. I couldn't cover everything. So, and I think, of course, inevitably, because it's one of the oldest events, for all sorts of reasons, which you can imagine, it's the least well understood. The quality of dating, the ability to correlate locations and horizons around the world, that kind of thing. But it does seem to be connected with a dramatic freezing and lowering of sea levels. And presumably these freezing effects were quite widespread. And so a lot of tropical type organisms would have died out.
I think we've had our money's worth. That was terrific. Thank you very much, Mike. You've given us a really good, plenty to think about, and it's been a really good session. So I suggest we can run away.
Mm-hmm. Thank you very much indeed.